Hello everyone, it's Mr. Mollicash, your favorite calculus teacher, and I'm back this week talking to you about, I think the last part of Unit 2 for the NC State textbook. We're definitely not going to be done with derivatives, but we are going to be done with Chapter 2 in the book after this video. So the last topic in this is about what we call related rates, and that's all I'm going to talk about in this video. So we have all these derivative rules now. We've talked about the limit definition, the power rule, the quotient rule, the chain rule, the product rule, all these rules, and it's time for us to start using these rules in an applied way. Like why do we care about derivatives, and why does it matter, right? So here's a really simple, I think, probably one of the simplest examples I've ever seen of related rates. So without any further ado, we're going to get going here. It says, at the moment the pebble hits the surface of the water, if you drop a pebble in a calm pond, like with, total glass, if you drop a pebble in it, it creates these ripples, right? These ripples appear in the water in the form of concentric circles. And you can see there's a little circle in the middle, and then there's bigger circles, and it keeps moving outward, right? And so we're going to assume that the radius of the outermost circle, I guess this one right here, the one that you can see the furthest out, is increasing at a rate of 3 inches per second. So there's the word rate. And the word increasing is also a very important word. And the fact that we're dealing with a circle, okay? And the circle's radius is what's increasing, okay? Let's read the last sentence. At the instant when the radius, there's that word again, when the radius of the circle reaches 20 inches, at what rate is the area of the circle increasing? Okay, so let's get this down to start with. If a first derivative of any kind, whether it's dy dx, dy dt, dh dt, any of those things, okay? If the first derivative is positive, is greater than 0, then that means that a quantity, it could be the y value of a function, it could be height, it could be something else, quantity is increasing. And if the first derivative is less than 0, then we say it's decreasing. The easiest way to see this is by looking at a graph, right? So if you have a function and we're looking at y values of a function, then when at a certain x value, if y's are getting bigger and bigger and bigger, then the slope of the graph, or the tangent line slope, the first derivative, right, is positive, right? And this is at the point xy. So at another point, say x2, y2, you might have a derivative that's negative. So this is pretty familiar to us, but we don't have to limit ourselves to just graphing x and y, right? So what I'm going to do is I'm going to illustrate how this whole phenomenon works with more practical problems, I suppose, like this one about the pebble in the pond, okay? Pebble in the pond problem. All right. And it's taken me a little while to erase all this stuff. I can't change the size of the eraser on this. I wish I could erase a lot faster, like I was in a real classroom or that kind of thing. But anyway, you get the idea. All right. So the reason I went through all that language with you guys is because, one of the words that I underlined in this problem, one of the words that I underlined is the fact that something is increasing, right? Okay, so what I'm going to do is I'm going to highlight here make my highlighter a little bit bigger. I'm going to highlight this sentence. The radius of the outermost circle is increasing at a rate of 3 inches per second. And what I want to do is I'm going to write that in calculus language. The radius, let me redo that because I didn't want that to be that big. Let's try that again. All right. The radius is increasing, so that means that the derivative of the radius with respect to time is positive, is going to be positive, and in fact it's going to be positive 3 inches per second. So every second the outermost circle is getting 3 inches more in radius. Okay. Now you might be wondering, like, what the heck? Where did the t come from? Okay, well, remember that the top quantity is measured in inches. That's the radius of the circle, right? And the bottom quantity is, this is a rate per second, right? Inches per second, and seconds are units of time, right? So it makes sense that we would use dr dt because the radius is what's changing every second. Okay. Now let's go highlight another one. We'll go look at the second sentence and see if we can maybe translate from words to calculus notation. Okay? All right. At the instant when the radius of the circle reaches 20 inches, let me change colors one more time. At what rate is the area of the circle increasing? All right, so let's go back to that blue sentence. That says at the instant when the radius of the circle has reached 20 inches. So when r is equal to 20 inches, comma, and I'm not going to use yellow writing, so I'm going to switch to black now. We want to find at what rate, so rate is something changing over time, the area of the circle is decreasing. So the derivative of the area with respect to time. Okay? So all these words that I've highlighted here really just come down to numbers and symbols. We know that dr dt is a constant positive rate of 3 inches per second. And we know that at some certain instant, at some snapshot like this picture here, the radius is 20 inches. At an instant. Now it's not always 20 inches, right? It starts out at 0 inches and it gets bigger and bigger and bigger. But at a certain instant in time, the radius of the outermost circle is 20 inches. We want to find this. Okay. Now, the reason why this section is called related rates is because there's two rates given in the problem. There's a rate at which the radius is changing, and there's a rate at which the area is changing. And what I'd like to do here is point out to you that these two quantities, the radius and the area, are related to each other, right? Because this is a circle. Okay, so the first thing we're going to need to do is write an equation. I'll go through these steps with you again in a moment if you're taking notes, so just hang on. Excuse me. We need an equation that relates a radius of a circle with its area. Okay, so this is our solution. And right off we need this. We need this equation. So think about that for a minute. Like, how do I relate the area of a circle to the radius of the circle? Is there some area equation I remember about a circle? And you probably do, right? That's the area of a circle is pi times the radius squared. You knew that, right? Okay. So what we're going to do to find this rate is we have to find the derivative of both sides of this equation. So, okay, what we're going to do is we are going to differentiate both sides with respect to t. Both sides with respect to t. So that means that the derivative of the left side with respect to t is equal to the derivative of the right side with respect to t. And I keep saying with respect to t because it's not dx or d theta, right? We're measuring quantities change compared to the change in time. So it's really important that I keep saying with respect to t. All right. Anyway, how do we write this? Well, this is, if you remember, the d dx of y or the d dx of f of x. You could just say a prime, but rather I'm going to write dA dt. This is going to say dA dt. And over here I'm going to do two things. I'm going to use the power rule, so I'm going to put the 2 in front with the pi, and I'm going to reduce that exponent by 1, so that's 2r to the 1, 2 pi r to the 1 rather. And then, because of the chain rule, I need to tack on the derivative of r, which is not 1, right? It's dr dt. Okay, let's slow down and think about what just happened. What's in here, I did the power rule, 2 pi r to the 1 times the derivative of r. And the derivative of r with respect to t is exactly dr dt. Alright, so now what we're going to do is, remember all this covered stuff, I'm going to start plugging in, right? I need to find this, so let me write that over here. I need to find this at the instant when the radius is 20 inches. So I'm going to do 2 pi times 20 inches to the 1 power. And then I have to do dr dt, which was also given in the problem. That's 3 inches per second, right? Okay, so if I multiply everything out, I have 2 times pi times 20 times 3. So let's see, I think, 3 times 2 is 6, 6 times 20 is 120. So this should be 120. And then pi, and inches to the 1 power times inches to the 1 power is inches squared, and then divide by seconds. And look what just happened. Area is measured in square inches. Amazing, right? Time is measured in seconds. So this is the answer to our question. We can say that the rate at which the area of the circle is increasing is 120 pi square inches per second. So that area is growing pretty fast. Okay, well, it's kind of a big circle if it's 20 inches in radius. Think about one of those 20-inch rims on a pickup truck or something, like it's that big. So, and if it's getting 3 inches bigger per second, you know, that circle's growing in its area pretty quickly. Okay, all right. So what I want to do now is I'm going to erase all this, so go back and rewind the video if you need to. But I'm going to do this again by looking at a series of steps. And I am borrowing material from a book that I wrote in 2015 and 2016. I actually wrote a calculus book. And this thing that I just pasted here is one of the things that I put in the book about related rates. Okay, now in NC State's book, this is section 2.7. In my book it was 3.1, but these are the steps that you should use in related rates. There are basically 5 steps in every related rates problem that you will ever encounter. Okay, so let's go back through these steps with the problem that I just did, and I'll just keep everything in pink. So in the problem given, write down an equation that relates the quantities that are changing. So the quantities that were changing were the area and the radius, and they're related by this equation, A equals pi r squared. Okay, so I did that. Now, not every problem is going to be about a circle. Sometimes they'll be about triangles, or they'll be about rectangles, or they'll be about graphs, or cones, or spheres. So you're going to have to go research, like, okay, how do I find the volume of a cone, or the surface area of a sphere, or the hypotenuse of a triangle? You know, that might be the Pythagorean theorem, for example. So you might find out that useful geometry formulas apply in situations like this, okay? But just kind of keep in mind that, like, not everything's about a circle, okay? All right, so we want to differentiate both sides of this equation with respect to t, which is exactly what I did, right? I did dA dt. And then the derivative of this with respect to t was 2 pi r times the derivative of r. And again, the chain rule applies there, right? The derivative of r is not 1. That would be the derivative of r with respect to r, right? dr dr is 1, but dr dt is not 1, okay? Not unless they tell you that it's 1. And that would be like 1 inch per second, not 1 inch per inch, right? Okay, so the third thing is write down in calculus notation the quantities that are given in the problem. So we knew that, for example, we knew that r was 20 inches. We knew that the radius was increasing at a rate of 3 inches per second, right? So we need to know that information from the problem so that we can do what? Substitute these into this is called the differential equation because it has derivatives in it. We'll talk more about differential equations in the future. But anyway, you plug these in, right? So we don't know our dA dt. We knew that our radius was 20 inches. And it's kind of like you're just rewinding the video again, right? And then dr dt is 3 inches per second. So now that we've, oops, sorry about that. Let's fix that problem. All right. I keep forgetting, let me see if I can put this up here. There's a little button on the side of this stylus, and if I press that button, it keeps that writing going, right? Sorry about that. Anyway, the last step is to solve for the desired quantity or derivative. And what did it want? It wanted the rate at which the area of the circle was increasing. And so the reason why this is a simple problem is because that's already solved for. You don't have to divide or multiply or add or anything. You just multiply all these numbers out and you're done, right? Now, it's important in problems like this to keep in mind that units are important. Units matter. So inches times inches, or inches to the second power. And when we say this in the United States, we say square inches. We don't really say inches squared, even though that's what we write down. Okay? All right. So I want to go through a little bit more of a more complicated example from my book, and then we'll kind of stop this video and we will kiss Unit 2 or Chapter 2 goodbye. Okay? And so, yeah, I've got problems in my book about person walking away from a lamppost, a ladder leaning against the side of a building. So let me see if I can just grab this one about the spherical balloon, because for my students, you're going to have a lab this week that has to do with something that comes from geometry that's kind of like this. So, yeah, let me just kind of grab that, and let's come up here and paste that problem. Okay, so let's see if we can work this problem out together. And what I would encourage you to do is to see if you can run through these steps. Maybe pause this video and work ahead. So see if you can do step 1 on your own, and then see if you can do step 2 and step 3 and step 4 and step 5. Okay, see if you can do that. So first, step 1. Now is your chance to pause the video if you want to try this on your own. Okay, so let's read this. A spherical balloon is being inflated in such a way that the length of its radius is changing at a constant rate of 2 centimeters per second. at the instant when the length of the radius of the balloon reaches 5 centimeters, how fast is the surface area of the balloon changing? So the good news is that that equation in step 1 is already done for you. The surface area of a sphere, my bad, is 4 pi r squared. So they gave you that equation. Sweet! Step 2. What are we going to do with this equation? We're going to differentiate it, right? So we're going to differentiate this with respect to time. The surface area is changing over time. And we're going to do the power rule. So this is going to be 8 pi r, and then times the derivative of r, which is dr dt. Okay. So I'm sorry, I should have paused a little bit to give you a chance to work that out on your own. Step 3. You can pause this if you want. See if you can work ahead. Okay. Write down in calculus notation the quantities that are given. So we know what's given in the problem is that the radius is changing at a rate of 2 centimeters per second. So we know that dr dt is 2 centimeters per second. And what else do we know? At the instant when the length of the radius of the balloon reaches 5 centimeters. So we know that the radius of the balloon is 5 centimeters, which is like 2 inches. You know, it's like a small balloon. 2 inches in radius, so maybe 4 inches in diameter. Still not very big. All right. What are we going to do with all this? Step 4. Now's your chance to pause. Okay. Substitute these things here. Right, so we need to know that we're going to plug 5 centimeters in for r. And yes, I'm putting the units in on purpose. And we're going to put the 2 centimeters per second in for our dr dt. And let's see, we're going to work this all out. So let's see, that's 10 times 8, which is 80 pi centimeters times centimeters per second. And let's match the units, right? Square centimeters would be a surface area, right? Surface area. So we solve for the desired quantity. We are done. Step 5 was already done here. We didn't have to solve this equation to get ds dt by itself, so we are done. All right, good. Let's see. We'll work out letter B. I'll leave C and D for you to think about on your own, and you can message me or comment in this video if you'd like to know, what I think about C and D. I never say this in my videos, but you can subscribe to my channel. All these videos are in the Calculus 1 playlist, and so you can get some good examples for Calculus 1, especially right now with derivatives. All right, letter B. So let's do step 1. Now, the volume equation is what's going on here. They already gave us that equation. Whoop, whoop. If they don't give it to you, you got to go find out what it is. So Google is your friend, or maybe your textbook. All right. And now I got to find the derivative of that with both sides, right? So this is going to be dv dt. I'm going to do the power rule. Now listen, 3 times 4/3, the 3's would cancel out, right? So I get 4 pi r squared. Why is it 4? Where do the 3's go? Well, remember, if I do 4/3 times 3, the 3's cancel, right? Okay, and then I have to do the derivative of r thanks to the chain rule. So the derivative of r is not 1. That would be dr dr. dr dt is something else, and it was given in the problem, right? So let's do that. Step 3. Write down in calculus notation the things that were given. We already did that in part A, but we'll do it again. So we know that the radius is changing at a constant rate of 2 centimeters per second. And and we know also that the radius is 5 centimeters. All right, so step 4, we're going to substitute both of those into our equation, right? So dv dt, now step 3 is substituting into step 2, right? So this is equal to 4 pi. The radius at this moment has to be squared, right? Pi r squared. And then the derivative of the rate with respect to time is 2 centimeters per second. All right. So step 5, what we want to do is we're going to multiply all this stuff out and solve for dv dt because they want us to find out how fast the volume of the balloon is changing. So this is already solved for. And let's see, this is going to work out to be 4 pi times 25 centimeters times centimeters times 2 centimeters divided by seconds. Yep, centimeters times centimeters. 5 centimeters times 5 centimeters is 25 square centimeters, right? All right, so we're going to work all this out. I think that turns out to be 200 pi. And what are the units for this? Centimeters times centimeters times, oh, yes, more centimeters. All right, there you go. The units match. We have volume units on top. We have time units on the bottom. We are done. All right, so a couple of examples there for related rates. These are pretty easy examples. They get a little bit more complicated. But hang in there. Reach out to me if you need some help. I am definitely on your side, and I want you to master Calculus 1. So until next time, have a good week.